this morning. And I want to look into that and thank you for coming. Tim Verbelen is if you were up early enough to see the keynote, you know that Tim is a leadership award winner this year. And Tim's got a little presentation for us about robots. And if you saw the OSGi demo, you saw a robot. So I'm going to not steal your thunder and turn it over to Tim.
Thank you, Dan. So today I'm going to talk to you on my research. I'm actually a researcher at Ghent University in Belgium. And my research is all about AI and robotics. So if you think about AI and robotics, you immediately think, yeah, the killer robots that will take over the world. And also if you kind of read any popular news article nowadays on AI, they're all like, yeah, robots are going to be super intelligent in a few years and they will do all kinds of tasks for us. But if you then think about the robots we can actually see right now in our houses, they're more like this, right? So are they actually that scary and intelligent? I don't think so. So if you have a vacuum cleaner in your own house, you might know it's not quite that complex an algorithm that cleans your house, and it's by far not the most optimal algorithm to clean your house. Exactly. So why is this so? Well, actually, the main reason is because if you're a robot that has to operate in an unknown environment that you've never seen before, then it's quite hard to do very complex behavior, because there are tons of things that you have to consider, and it's very hard to program such a thing even to do this simple behavior. So on the other hand, if you want to have some robot that does something very complex and does it very fast, then you're at the entire other end of the spectrum. So you need to back down on the environment complexity, make sure you can control everything, and then make sure that your robot does this very specific tiny tasks it ought to do very fast and program it that way. But if the environment changes slightly bit, then you're off and you have to reprogram it all over again. So of course, the question is, how do we get to this perfect corner? And of course, self-learning robots might be the way to get there, right? So if you have a robot that can say, your goal is this, and figure out yourself how to do it, and it works, then it would be great. But reality check shows us that we are actually here if we are talking about self-learning robots. We have to do very simple tasks still, and in a very controlled environment, and if we can then get the robot to learn something by itself, it's already gone, yay, good accomplishment. So I'm going to talk to you about a bit on what I'm working on right now and where we're at. And first of all, of course, before you can make the robot learn, make it do something, you first have to control it. So that's the first part. And I've been using OSGi for about 7 years now in my research. So throughout the talk, I will cover some of the very nice things that OSGi offers you to make life much more easy to do all these kinds of stuff. So this is our robot. You might have seen it maybe in a slightly different constellation with 1 or 2 fingers less at the demo stand. But so basically it's a mobile-based platform that you can drive around. On the front we have mounted a LiDAR sensor, which basically gives you an estimate of the distances in front of the robot. And it also has a 5 degrees of freedom arm and a gripper. But the real fun stuff is inside there, because we actually tear down the robot when it got delivered. We pull out everything inside and we put in an NVIDIA GPU board, which basically gives us quite some compute power if you want to do some AI stuff on the robot. And to control especially in research, it's often they use the robot operating system. So it's basically a set of libraries that help you to create robot applications. So it's basically a generic message passing framework. You can think of it like MQTT. So you can subscribe to topics, publish to topics, but leaving the message type unspecified. They also request you to, if you have a topic, you need to specify which is the type of message you will send on the topic. So it's a bit in between MQTT and something that's type safe. And it also gives you a lot of kind of utility libraries, for example, to give you a description of the geometry of your robot, or to do inverse kinematics or forward kinematics calculations. And the nicest part, I think, is that it also interfaces with a lot of simulators. So you can also control your robot inside the simulator, and it also supports a wide range of robots and sensors out of the box. So there are lots of already available modules that allows you to control many of the robots that are around. But of course, we would like to control our robot in OSGi. So how do we do it? So ROS basically has this kind of master nodes. They call the ROS core. And then you can, for example, have a controller for your robot. And at the same time, you can also have a controller for the same robot inside your simulator. And the way it works is by publish subscribing to a certain amount of topics. So for example, you can publish a command to this topic to control the position of the arm, for example. Or you can send a command to this topic to set a velocity for the base platform. And also you can subscribe to a topic, for example, to get constant updates of where are all the joints of the arm, in which position are they right now. And besides that, there are all a bunch of additional ROS nodes, for example, to read out the sensor, or to do all kinds of stuff, to calculate an inverse kinematic solution, for example. So this is basically the ROS stack as you would use it if you're just using plain ROS. Now, one of the problems here is if you don't want to do a high-level control of your robot, you can say, I publish to the position command, but then what happens? How do I know it's finished? You don't know. You basically have to track the states and figure out, is the robot arm where I want it to be? I don't know, not yet, maybe. So it's kind of tedious to just use a pub sub command system to control your robot. It's doable, but it's quite a hassle. And adopting the OSGi concepts, I would rather have like a service for the robots if it's there, and I just call a method, say, set the positions of the arm, for example. So I want to use it in this kind of service-based system. So what we do is basically we have this library ROS Java, which basically allows you to talk to this ROS core, and from that you can then have our bundle that you configure, and you say, for this UBot bundle, I need to make sure that I listen to these topics and I can send commands to these topics. So this is the configuration information you give it, and based on that, it can then give you a nice service, for example, a service for the arm, to control the arm, and a service for the omnidirectional base platform. And this also allows you, if you have a different arm from a different robot, to access it these services. And if you deploy and configure your robot, this service will pop up, and whatever program you have can actually consume the service and control the robot the same way it would use any other arm or base platform. And also we have kind of configuration bundles in OSGi that basically configure all the additional ROS stuff for you. So you can basically use OSGi configuration that will then spawn whatever ROS thing you need, because the ROS stuff is typically running inside its own process. It's C code or C++ code. So you can basically now configure this from OSGi, make sure the correct process will launch, and everything's up and running there. Now, of course, what do we want to have in these services? What are the kind of methods we want there? And for example, an arm could be something like this, where you could set a position for one joint, or you could set a position for all the joints at once, or you might want to do some inverse kinematics and say, I want to move the tip of the gripper to this X, Y, Z coordinates in Cartesian space. And again, so the question is, when do you return these things? Do you wait? Do you block basically until you're at that position, or do you return immediately and then you're on your own to figure out when you get there? You have to sleep a bit, for example. So it's a bit tedious. How do you get it right? No, exactly. So fortunately, OSGi R6 gives us the promises, and this allows you to basically do both. So what happens is, if you call set position, you get a promise, and this promise will resolve whenever the arm is at that spot. And the nice thing, the promises, is also that you can chain them and say, whenever we get to that position, then I issue my next command. So if you look at what your consumer bundle looks like then, so this is kind of a basic controller for your robot arm. You just annotate it with the awesome DS annotation. Say, I have a component, I want to control an arm, so whatever arm service comes up gets injected right there. And then if you want to do something, you can say arm dot open the gripper, and then you say dot then, and then because the promise will resolve with the arm that you were controlling, you can use the promise to get the arm back and then issue your next command. You can say if the gripper is open, then move the arm to this position. Then also I want to like the elbow joint to make sure it's in the correct orientation, and then I want to move it a bit down and close the gripper. So basically this is the code you use to open the gripper, move it to some place, close the gripper, and then you can issue your next command to kind of do whatever you want with what you had. And the cool thing is that where the comment is, here it immediately returns you, so you can do whatever additional work, you can process sensor information, or you can do whatever you want, and then if you want to wait for some of these things to resolve, you just get a promise and you do the get value, and then you have the blocking behavior in case you would want that. So it's a very cool way to kind of fluently program your robot arm this way. Now, what about the omnidirectional base program? Because there you will set a velocity. So you can say start moving with this velocity, and it kind of immediately, right? So you say start moving, and once it starts moving, your promise will be resolved. So what is the use you could ask for such an API here? So for once, it's to have like this nice coherent APIs for all our robot things. But another thing you can do is then a convenience method, for example, until. And what this method does is you give it another promise that's kind of a condition. And whenever the condition resolves, then you resolve the until method with the omnidirectional base instance. So how can we use that, for example? So again, we have our simple DS component. And what we can do now is we have the base. We start moving it with an angular velocity, so it will kind of gradually move around. And we have this other method that pulls the LiDAR sensor. And whenever the LiDAR sensor detects something, this will resolve. And so then you can use it in your application, like start moving the base until the LiDAR sees something, and then you stop it. And then you're kind of at the position where your LiDAR sees something, and then you can, for example, issue a grip action or do whatever you want. So it gives you a nice fluent API, again, to also control the base. So I think this is a very nice way to control your robot, much nicer than issuing command on a topic, and then I have to subscribe to various topics to figure out what is the robot actually doing. Is it actually doing whatever I want to do? So now we have our robot in place, we can control it. Let's try and teach new tricks. And so the trick at hand will be fetching objects. So why do we want to learn the robot to fetch objects? Well, basically it's a very narrowed down task. It's very clear what it should do, but on the same hand, it's still having some kind of complexity. First of all, you have to process sensor information. You have to detect whatever the target is you're heading for, and then you have to make sure you learn how to drive towards it and make a grip for it. So if you break it down, it's a non-trivial task to do, but still you can kind of issue it in a very controlled environment to do experiments with. So this is basically our setup in the lab. So we have our robots, we have a soda can somewhere in this square, and then let it go nuts, and hopefully it will learn in the end to grab the can. That's the goal, and we don't want to give it any about how the robot or something. It just has to figure it out by himself. And therefore we use this technique called reinforcement learning. So basically you have the environment, which is basically everything is beyond your control, and you have your agent, which is basically the robot. So basically what you do is first your robot will get an observation. In this case it will be sensor values from the LiDAR, and from this observation it then has to figure out what am I going to do. So you do some action on your environment, and hopefully the environment is able to give you some feedback as a reward signal. And if you're doing good, you get lots of reward. If you're not good, you get negative reward or even punishment. So using this signal, you then basically have to learn what are the actions I should do to actually reach my goal. And we use deep reinforcement learning, meaning we use the hyped neural networks for that. So basically the agent is basically a neural network that we feed in the observations and out come the actions that the robot should do. And then we use the reward signal to train this neural network in order to gradually improve it, and hopefully we will end up with a robot that is able to locate the can and drive towards it. So here you can see, for example, an input from the LiDAR. This is fed into the neural net, and then out come the action you can do. You can move left or right, or go forward or backward, or turn around, or maybe you're pretty sure you're standing next in front of the can so you can safely grip it. And the reward signal we issue is that we give it like the negative distance to the can. So basically, we're not giving it a kind of reward, but we constantly punish it, and we punish it less the closer it gets to the can. And this is basically what we then use to train the neural net. So basically, in a nutshell, what does the formula mean? What we try to estimate is what is the future return I will get if I, in this state, do this next action, and what will be the estimate future return I will ever get from doing this action right now. And basically, if you know that, then you can always choose the action that will end up giving you the best estimate return in the future. So, how does it work then? Because, of course, you don't want to have a robot doing random actions in your lab. So you start off running it in simulation. And the nice thing about a simulation is that you can scale it up. You can have many one of those robots in parallel, because as you can figure out, it takes a lot of trial and error before it actually learns to do anything sensible. So by scaling up the simulation, you can basically learn faster from many robots' experiences. So everything is then stored in what we call an experience pool, and that we then use to learn parameters for the neural net. And every now and then we sync this in a central repository, which will then update all our simulations. And by going through this loop over and over again, you end up with a robot that's constantly improving in simulation. And once you find yourself quite happy with the result, you're pretty confident, then you can also deploy the neural net on your real robot and see what it does. So to implement all this, we also, of course, use OSGi. So we have our Diane platform, which we use for coding neural nets. So it's all in OSGi, everything is nice, OSGi service, and we actually build on top of Torch. So it uses all the native code from the well-known deep learning framework Torch. So we are on par performance-wise with whatever other framework is there, but we have kind of all the nice features from OSGi. We can distribute components around using remote services. And we also have a web UI that you can use to quickly prototype and experiment with it, which is pretty important as a researcher, that you can quickly submit experiments and see the results as they come by. So, proof of the pudding, what did the robot learn? So here you can see actually our UI in action. So this is basically the configuration of our neural net, and we will now deploy this thing onto the robot. So what we're doing now is basically sending the configuration to the OSGi framework on the robot. And now every building block of the neural net is basically an OSGi service. And using the service references, you can basically link them together at runtime. And by now we connect the LiDAR input to the input. So this is how it's on the time. And we send the output to our robot service that is the Promise API I just showed. And the output is that it estimates return in the future. And if it then chooses the action to actually which it estimates to be the best rewarding action in the future, you see it actually learned to go towards the can and pick it up. Yay! We have a self-learning robot. Now, of course, the question is, it can only see in front of it. So what will happen if the can is behind the robot? Well, this is what happens. So it can basically not see any can. What it has learned is, I should drive backward. Increase my field of view, and maybe the can will pop up. That doesn't happen, and at a certain moment I think, yeah, the robot says, I should not go any further backward because I've learned the size of my cage I'm in, so I will totally destroy it if I go further backward. So it has learned some things, but it hasn't learned to explore, to see what's behind the robot. So how can we fix it? Well, one thing we can do add some more sensors. We are living in the IoT age, so just put some sensors in the corners of your environment and also feed these into your neural net. So this is a very cool concept that we are exploring. And what you can then also do is kind of deploy these building blocks like in the edge. So you don't have to send all the raw sensor data to the robot over Wi-Fi. You can just pre-process it on whatever server you have next to it, wired to the and send a tiny amount of information to your robot, which it can then use to estimate what it sees behind it or whatever it sees in the corners. And this basically goes from the traditional deep learning where everything is just like one black box to kind of starting modularizing also your neural net into small pieces and parts that you can actually maybe reuse later in another use case, for example. So this is then what happens. So in this case, you can see we have like these 3 processing pipelines which will process the things for each of the sensors. So now again, we first deploy everything onto our robot, but then we figure, yeah, for the environment sensors, we can just move them over to the edge. And this is basically using remote services. We just move the bundle, or basically just move the configuration to another runtime, then the service pops up over. And if it sees, yeah, the next one in line is basically on a different platform, it just uses a remote service, remote method call. So now again, we connect all the sensors to it, and we will connect the output to our robot, and then hopefully it will be able to see what's behind it. So ta-da! So now it first has to move a bit around, because also it will also see itself, for example. So it moves around a bit, and then it can detect, oh, I'm moving, I see this happening in the sensor input, but this thing stays the same, which is behind me, so maybe I should turn around and take a look there. And so once the can comes in the vision of its front-facing sensor, then again it kind of turns over and goes straight to its target and picks it up. So this is actually pretty cool that the thing learns all by itself how to process the sensor information into actions and do something, well, I wouldn't say useful, but at least do something, right?
We have some components now.
And this is actually the reality. This is where we are in research on self-learning robots, when you have no prior knowledge whatsoever and it has to figure out everything by itself. So you shouldn't be having nightmares about to kill robots just yet. You're pretty safe now. So with this, I can conclude my talk. Thank you all for joining. Do not forget to evaluate the sessions. Feedback is always greatly appreciated. So thank you. If you're interested in the own framework, there's the URL right there where you can find more information or the source code on GitHub. If you want to know more on how do you train a neural net, what is it about, I have another session just before lunch. So if that's it, feel free to join. And maybe there are some questions still.
Any questions for Tim? Tim, how long have you had the Java AI library for the robot to interface to ROS? Is that just the past year?
I think we have it 1.5 to 2 years maybe now. We first started, I think, 2 years ago, but of course the promises came in later, so that might be a year ago or so. Yeah.
So is an OSGi framework running on the robot?
Yeah.
And that's cross-standard?
Yeah, exactly. But you can use any framework, of course. There is no, I think, definite standard for controlling robots. There are some initiatives like the ROS operating system is one of them, but also the big companies, the industrial companies, they usually have their own system to control their robots, of course. But there's no kind of de facto standard. In research, ROS is very popular. I don't know what lives inside the industrial companies, but I think they have their own. we only use our robots for doing research purposes. So we're not kind of, our mission is not to integrate every robot around and build a system around it. We're just kind of, we have this robot, we want to interface with ours. So how do we get the job done, and how do we think is an elegant way to do it? So it might be challenging if you go, it's kind of the IoT story. How do I integrate each sensor around there? And it's a very difficult task to do. I think you need to be a big industry company to actually get that done.
Same is right to assume, though, because you have the knowledge that you build with promises, that it's really the mapping to the local that you control.
Yeah.
That's where all the work would be.
Yeah.
Mapping
Yeah. Exactly.
native to your model.
Exactly. Yeah.
Okay.
So actually, Kuka is using control, but I forgot how they call it, but they already have the vision to modularize basically their software environment. Because I mean, they basically have the problem that even car manufacturers are saying, I don't want to do robots anymore because I'm not flexible enough. Yeah, and that's why they look into OSGi to make this easier and more flexible.
Yeah.
Is the PubSub mechanism based on BBS, or is your own implementation?
So the PubSub system is basically the ROS stack you subscribe to topics, how you publish topics, and the format of the topics. There are some standards by topics, for example, to how do you send velocity information to a robot, but for other stuff, many of the robot manufacturers also define their own kind of messaging. So it's also their kind of a hell where what is exactly the message I need for this robot. So you actually need an abstraction layer anyhow to translate to every robot.
So that actually stores very similar to DNF, where you separate.
Well, it can do both, I think. So ROS can do both. So you can have all the instructions on a single machine, but
Have it converted from the existing layout.
and then have to do the PubSub mechanism. But that,
Is it correct to say that the PubSub mechanism is specific to this robot, to this brand of robot, and their?
no, it's specific to the ROS stack to control the robot.
Oh, okay.
Yeah.
Any other questions? Thanks.